Okay, let's solve this question. A point moves with deceleration along the circle of radius r so that at any moment of time its tangential and normal accelerations are equal in modulus. Okay, a point is moving along the circle of radius r. Suppose here's the point, and its normal acceleration and tangential acceleration, its normal acceleration and tangential acceleration are equal in magnitude. Okay, so basically a tangential is equals to a normal, which is centripetal acceleration. Okay, so we can write as a tangential is equals to v square by r. Okay, this is one thing. Another thing is, at initial moment t is equals to 0, the velocity of the point is v naught, and at t is equals to 0, velocity is equals to v naught. Okay, this is given. Alright, we need to find the velocity of the point as a function of time and as a function of distance covered s. Okay, so let's find the velocity of the point as a function of time first. तो उसके लिए क्या करेंगे, ए टी को हम ऐसे लिख सकते हैं डी वी अपॉन डी टी, विच विल बी इक्वल्स टू वी स्क्वायर बाय आर. वी कैन टेक v in the denominator, dv by v square will be equals to dt by r. Take integration both the side. dv upon v square is equals to integration of dt upon r. When you integrate this, you will get v to the power minus 2 plus 1 divided by minus 2 plus 1, and then the limit will be v naught to v final, because v naught is the initial velocity, and in this we get t by r from 0 to t. Okay, from this we will get minus of 1 upon v naught to v final is equals to t by r, which will becomes minus of 1 upon v final plus 1 upon v naught will be equals to t by r, and 1 upon v final will be equals to 1 upon v naught minus t by r. So from here, taking LCM, 1 upon Vf is equals to V naught R minus V naught T. So Vf final is equals to V naught R upon R minus V naught T. We can take R common from the denominator, so V final will become V naught R upon R times 1 minus V naught T upon R. We can cancel R and we get V final will be equals to V naught upon 1 minus V naught T upon R. So this is our final velocity as a function of time. Okay, now we need to find the velocity as a function of distance. Okay, same thing, we can write this as dv upon ds times ds upon dt, because we can cancel ds out and we left with dv upon dt is equals to v square upon r. Okay, and we know ds upon dt is what? V. So this will becomes v dv upon ds is equals to v square upon r. You can cancel one v with another, and you're left with dv upon v is equals to ds upon r. Taking integral both the side, dv upon v is equals to integration of ds upon r, which will becomes integration of 1 upon v is ln v from v naught to v final is equals to integration of ds is equals to s, and r is constant, from 0 to s. You will get ln v final minus ln v naught is equals to s by r, and using the property of logarithm we can say that ln v final upon v naught is equals to s upon r. From here you get v final upon v naught is equals to e to the power s upon r, or v final is equals to v naught e to the power s upon r. So this is our velocity as a function of distance. This is part A. Now part B is the total acceleration of the point as a function of velocity and the distance covered. Okay, so we know that the total acceleration at will be equals to the magnitude of tangential acceleration squared plus magnitude of normal acceleration squared. As they both are equal, we can write a tangential is equals to a total is equals to 2 times a tangential squared. So a total will be equals to under root 2 a tangential, which will be equals to under root 2 what is a tangential, v square by r, and in place of v we need to write it in as a function of velocity and distance covered, right? So we can write v square as this expression that we got. So vf is equals to v naught e to the power s upon r. Okay, so we can write v naught e to the power s upon r squared upon r. So a tangential will be a total will become under root 2 v naught square e to the power 2s upon r, which is our answer.